Welcome to Mission Control. I am your flight director for today's explainer simulation, and we are locking our radars onto one of the most volatile, high-stakes orbital paths in the entire Cambridge AS and A-Level Mathematics 9709 syllabus, mechanics. Specifically, the precise engineering required for resolving forces and finding resultants. If you treat this material lightly, it is incredibly easy to suffer a rapid, unscheduled disassembly, tumbling down into the lower grading bands before you even clear the atmosphere. But if you approach this unit with the hyper-focused, calculated precision of a rocket systems engineer, this exact topic becomes your ultimate launch propulsion system, rocketing your score to maximum yield. Today, we are running a full-scale interactive exam launch simulation. We are going to monitor the data telemetry, deconstruct the official examiner expectations, and ensure your strategic flight layout is perfectly calibrated with absolutely zero margin for error. Buckle up, cadets. We are initiating the launch sequence right now. Let's start by looking at the main console. I've pulled up a direct transmission from the ultimate flight inspectors themselves. A senior examiner literally stated, "The difference between a B and an A star in mathematics often comes down to how well you understand mechanics, resolving forces, resultants." Now you might be wondering, why is this specific module the ultimate gatekeeper? It's because pure mathematics requires abstract logic, but mechanics forces you to map that logic onto physical, dynamic reality. You aren't just moving numbers around. You are actively managing friction, tension, weight, and applied thrust. If your vector resolution is off by even a single degree, your resultant force is completely corrupted, the mathematical trajectory decays, and the entire calculation crashes. The examiners know exactly where your structural weak points are. Our mission today is to reinforce those vulnerable areas and lock in your high-tier marking bands before you ever step foot into the exam hall. Here is our locked-in, heavily structured flight plan to ensure we capture every available mark. Phase 1, core principles. Phase 2, the procedural framework. Phase 3, top examiner warnings. And finally, Phase 4, advanced strategy.
Initiating Phase 1, Core Principles. Let's calibrate the launch track.
I am projecting a complex, multi-part Cambridge past paper question onto the central viewing monitor right now. Consider this our target orbit profile. To reach it, the syllabus demands you demonstrate a, quote, connected conceptual understanding. Let me translate that from examiner speak into mission-critical reality. This means you cannot just memorize a standard low-altitude descriptive trajectory. If you just remember the standard textbook setup of a particle resting on a smooth horizontal plane, you are going to stall out. Cambridge tests your elite evaluation metrics by dynamically changing the physical parameters. They are going to throw an evaluative launch pathway at you, something like a system of connected particles suddenly placed on a rough, inclined plane, with a driving force applied at a bizarre 30-degree angle. If you rely on rote memorization, that system shock will trigger an immediate failure alert. True mastery means taking the foundational principles, like Newton's second law and the precise laws of limiting friction, and dynamically transferring them to whatever unfamiliar environment the examiners throw onto the flight deck. And this brings us to a massive system-wide debate: analytical depth versus superficial breadth. Over at our simulations propulsion console, we've got engineers who constantly want to overload the system with raw fuel logs. They read a question, panic under the clock pressure, and just start dumping raw facts, formulas, and data definitions onto the page. They're burning way too much energy trying to cover superficial breadth, hoping something magically earns a mark. But right next to them, at the navigation station, our layout specialists know better. They know that if you steer incredibly fast but ignore the structural boundary coordinates, meaning you completely miss command word constraints like show that or hence, you trigger an immediate system failure on the examiner's dashboard. Cambridge prioritizes deep, rigorous, analytical logic strings. We cannot just burn fuel. We have to establish a direct, analytical pathway to secure those high-tier marking bands before our time hits zero. Which opens up a very real telemetry issue. Why do so many highly capable students totally crash during multi-stage analysis? It comes down to a complete misunderstanding of the method mark strategy. In our mission control, method marks, or M marks, are your telemetry data. If you resolve your horizontal forces perfectly, but make a tiny arithmetic error calculating the final thrust, Cambridge can still award you the method mark, but only if your analytical logic string is highly visible and mathematically sound. Students struggle because they fixate entirely on the final accuracy mark, the A mark. But listen to me carefully. If you do not map out your step-by-step thought process for the examiner to clearly verify on their radar, a single dropped negative sign will trigger a total mission abort, and you will lose every single point. You absolutely must show your working telemetry. Phase 2, the procedural framework. It's time for the peer telemetry coordination debate. We are running a simulated clock right now, and the pressure is on to engineer an unshakable model response. My virtual propulsion engineer, Alex, is shouting to just start calculating the vectors immediately to save time. But Sam, my navigation specialist, is hitting the abort button on that idea. Sam is fighting to run through these exact 5 standardized steps, and as your director, I am backing Sam's protocol 100%. Step 1. Identify key elements. This means drawing a massive, clear force diagram. If you do not map out your weight, normal contact force, opposing friction, and tension visually, you are flying blind. Step 2. Apply relevant principles. Look at the data. Is the system in equilibrium, or are we experiencing acceleration? Decide immediately between F equals 0 and F equals ma. Step 3. Execute with clear working. Decouple your horizontal and vertical vector components using sine and cosine functions. No mental math here. Put it on the page. Step 4. Verify results. Check the telemetry. If your calculation outputs a negative tension in a simple string, does that make physical sense? Absolutely not. Strings cannot push. Recalculate. And finally, step 5. Present in appropriate format. Always output your final coordinates to the exact significant figures demanded by the Cambridge parameters. This protocol only works if you enforce strict reporting conventions. Your examiner is trying to read your flight data, so proper headings and correct terminology are non-negotiable. If you lazily refer to a reaction force just as force, without specifying, or if you mix up mass with weight in your equations, your signal gets lost in the static and the points vanish. Clear annotation on your working out is vital. If the examiner cannot clearly see the moment you extracted the coefficient of friction from the text to establish limiting equilibrium, they cannot legally award you the method marks. Your communication must be razor sharp. Phase 3, top examiner warnings. We are hitting mid-mission turbulence. Launch trajectory hold. Before we deploy our final paragraph structures to clear orbit, we need to optimize your educational flight deck. Take a second right now to subscribe to Ace the Exams at Ace the Exams and enable all notifications so you never miss our weekly flight-tested exam hacks, whether you are launching at IGCSE, O-levels, or ASNA levels. Hit that notification bell. Okay, hold is lifted, but warning klaxons are sounding. We are looking at classified intelligence straight from the principal examiner reports, and these 3 structural data losses are where missions are terminated. First, confusing cause and effect. Cadets constantly plug numbers into F equals ma, without realizing that acceleration is the result of the resultant force, not a force itself. Never draw an acceleration arrow touching the particle like a force vector. Second, forgetting presentation formats. Leaving a final answer in an exact surd when 3 sig figs were explicitly requested is like landing on the wrong runway. And third, the ultimate system killer, providing generic textbook answers that are completely detached from the specific context. I am overriding the main console to highlight this exact malfunction. When you lose your evidence links mid-paragraph, your response structurally collapses. To stabilize the text flow live, you need to deploy the Peel Framework power-up, point, evidence, explanation, link. Make your mathematical point, support it with evidence from your specific vector resolution, explain the physical principle at play, like limiting friction, and most importantly, link it directly back to the exact masses, angles, and coefficients provided in the scenario. By tethering your generic mechanics knowledge directly to the variables on the screen, you prove to the examiner that you are actively piloting the system, not just reciting an operations manual. Phase 4, Advanced Strategy. Time to take manual control. I am handing the simulation controls over to you. Welcome to the Interactive Viewer Controls Arena. We have a live radar check challenge. Challenge 1, the Visual Radar Sweep. When you extract data from a complex case study, you must follow this exact timeline. Let's focus on Step 3, solving systematically. Here is an elite navigation hack. When faced with an inclined plane, tilt your internal axis of resolution to align perfectly with the plane itself. By doing this, you instantly eliminate the normal reaction force from your parallel motion equation, saving massive amounts of calculation time. Challenge 2, identify the logic malfunction. Look at Step 4, checking for reasonableness. Imagine a flawed student response calculates a frictional force that is substantially greater than the forward driving force, yet their final sentence claims the particle is accelerating forward. Spot the malfunction? Friction strictly opposes motion. It cannot independently generate forward propulsion. Spotting these physical logic failures live is what pushes your launch propulsion meter into the A-star zone. Finally, if the mark scheme demands you evaluate and compare alternatives, say modeling a trajectory on a rough surface versus a smooth surface, Your comparative analysis must be airtight. You have to clearly identify both similarities, like the weight vector remaining constant, and differences, like the sudden absence of the opposing frictional force. Use strong comparative connectives to steer the logic. For example, whereas the rough plane yields an acceleration drag of 2 meters per second squared, the smooth plane, and then support it with your freshly calculated mathematical evidence. Draw a firm relative conclusion. Do not leave the examiner guessing. Tell them exactly how the physical outcome changes.
Phase 5, Summit reached, mission complete.
I am looking at the telemetry, and our propulsion meters have successfully peaked at a maximum A-star reading. Incredible work! Let's distill this entire simulation into 3 universal rules to take back to base. Rule 1, the 3-step question scan. Decode the command words before you ever touch the calculator. Rule 2, the fuel budget allocation. Pace your timing so you don't burn 10 minutes over explaining a 2-mark resolution when an 8-mark heavy lift problem is waiting on the next page. Rule 3, the post-launch system review. Always check your final accelerations to ensure they make physical sense in the real world. Now it's time for your next mission. Subscribe to Ace the Exams at Ace the Exams. Click the notification bell right now for our weekly grade masterclasses, and drop a comment below sharing exactly which Cambridge subject and level, whether it's IGCSE, O-Level, AS, or A-Level, you are preparing to conquer next. Flight Director signing off. I'll see you in the next simulation.